All right, here we go. So, beginning of chapter 10, it starts off with by stating that in another area of inferential statistics involves determining whether a relationship exists between two or more numerical or quantitative variables. For instance, is there a relationship between a person's blood pressure and his or her age? Or is there a relationship between the size of a house and its appraised value? Obviously, these two answers are what? Yes, you could probably argue the blood pressure and age because you could probably find some outliers that are pretty high up there but have really good blood pressure. And you can find some people out there that are real young that have really high blood pressure. And same thing with the house and appraised value, depending on what county you're in. You could have a really big house here in Texas, and it'd be like, I don't know, like 300,000. But then you can have like a one bedroom apartment in California, and that's also 300,000. So it just kind of depends on location. So you could argue these cases if there's a relationship or not. But in general, I do feel like they both would have a relationship. But we do have a formula that we could figure out if there's a relationship in a correlation style in a certain area. All right. We will investigate whether there is a linear relationship. And we usually always start with linear because it's either going to be a positive relationship, a negative relationship. A negative relationship is still a relationship, or there's no relationship. A lot of those no relationships could end up being a non-linear relationship. So it could be like a quadratic, exponential. You can almost see it with the scatter plot, see what it's doing. But we'll start off with just the linear. So a linear relationship between the variables. If so, what is the strength of the relationship? So you can have a strong or weak um, relationship, either positive or negative. Basically, just that means just on the scatter plots, how close are the dots together? If they're really close and pretty much make a perfect straight line, obviously that's going to be a very strong correlation. If they're really spread out and it's kind of hard to tell they're going up, but you can tell it's kind of going up, then that's a weak positive correlation type thing. So that's all that really means. And then it says what type of relationship does exist, meaning positive, negative, or no. You think we will write relationship one more time? And what predictions might be made from the relationship. So once you determine what kind of correlation it has, then you can determine what kind of regression line it has. And then with that regression line, we can predict what will happen in the future just off of what's happened in the past. Right? So this is a lot of, again, if you become a statistician, you do this part a lot as well. So rejecting and not rejecting is hard, but it gets easier the more statistics classes you take because that's pretty much the same recurring theme every single class. So you pretty much have learned all statistics, then you're just doing it over and over again. It's at least my feeling about this course. Even though this might be an elementary statistics, I do feel like you've pretty much learned everything there is about statistics. There's some other things you can apply, but you pretty much learn the main objectives. So in 10.1, we're going to talk about scatter plots and the correlation between them. So we'll show you how you can draw a scatter plot for a set of order pairs. I'll also show you how the calculator can draw a scatter plot for you as well. Some of y'all might recall how we do that once I show you again. So in simple correlation and regression studies, data from two numerical or quantitative So remember, quantitative is still numbers. Cannot do a correlation on qualitative data because we do not have, can't put words in a graph, right? We only got numbers. So it's either numerical or also known as quantitative. Variables are collected to study whether a relationship exists between the two variables. The data are collected as ordered pairs. So for an example, I could take your age and your blood pressure, and then that would be your ordered pair, and you would have a column of ages and a column of your blood pressure, and then that's what I'm trying to determine if there's a correlation with that or not. So there's always two things that you can have to determine if it's a relationship. In more advanced style statistics, you can have multiple columns, but to determine if there's a relationship, you're still only going to be looking at two columns at a time. So a lot of statisticians will take two things to see if there's a correlation, then take that correlation and see if there's a correlation between two different correlations. So it can get kind of advanced, but for y'all's purposes, they'll probably just stick with just two different variables, and you're just determining, is there a correlation, yes or no? Is it positive or negative? And then if it's strong or weak, it's kind of the gist. All right, so here we go. So one variable, just like in algebra, is typically the independent variable, and the other is the dependent variable. So if your argument is your age depends on, or your blood pressure depends on your age, well, then your age is independent and your blood pressure is dependent. So there's always one that's depending on another to determine if there is a relationship there. The independent variable can be manipulated. So we learned this a few chapters ago. I can change something about the independent variable, and it is known as the exploratory variable, and is also used as the x. The dependent variable cannot be controlled or manipulated. All right, so the dependent, you're going to change something with the independent, and then whatever that change will then adjust that dependent depending on what you did to the independent, because that's what you're going to be trying to test. All right, and again, this was known as the response variable, or also known as the y. Again, I think we did this in either chapter 1 or 2. If you need to go back and check that out. All right. To kind of finish up the rest of these words. The researcher will always decide which variable will be considered the independent variable and which will be the dependent variable. Again, a statistician could argue that the blood pressure dictates the age that you might be, but then you would flip that, but you would still have an independent and a dependent depending on what you're looking for. And again, the researcher will always be like your word problem. You don't get to make that decision yourself until you start working in the real world. So again, the researcher decides which variable will be considered the independent variable and which will be the dependent variable. Sometimes one variable can be assumed to affect the result of the other. For instance, the hours a student studies for an exam is likely to have an impact on the percentage of correct answers on the exam. In this case, the hours studied would be the exploratory variable, and the percentage of correct answers would be the response variable. However, when considering the relationship between one's income and one's height, it is not clear which should be independent and which should be dependent. So the determination there is kind of arbitrary. It can go both ways because you have no idea kind of what the researcher wants to do. So that would be arbitrary. Well, the researcher's gonna have to tell you what it is, because that one's not an obvious thing. Obviously, if you're a tall person, you're gonna make more money than a short person. I mean, hello? Yes. Yes. I don't know however long it would take. I would, yeah, I don't either. They have 7 hours to take the test, but it could be 2 hours like they did today. Well, I'll only have that fifth and sixth. I wouldn't have a seventh or eighth. All right, sounds good. Thank you. Bye. Yes. You don't know that because it could be. I could argue too that the more money I have, the taller I am, or it could be depending on how tall I am, I make more money. So it's really hard to determine which one's independent or dependent because it can kind of go both ways. Oh, but you can if there's a correlation to it. You would have to do a study to determine that. I would have to take everyone's income as my independent and then take the height as my dependent and see if there's a correlation. I could also flip that. I could take someone's height and their salary to see if there's a correlation that direction as well. Because you might find out that one way is not, but the other way is. So it could be that if I did the study, it makes more sense that it actually doesn't make any sense at all. You might find out to me, I don't think there's any correlation either direction you go with this, but it depends on where you pull your study. It could be a company out there that really likes tall people and promote them up, or they might like short people and promote them up. It's kind of hard to tell. Do it. Who's that? Oh, yeah, yeah, yeah. The tall people or something. There you go. So something like that. And it could be a case too that become a legal case where someone's like saying, hey, it's biased. I didn't get the job because I wasn't tall, or I didn't get the job because I wasn't short. And that's when a statistician would come in going, well, the numbers say this. There is a correlation. You do send higher tall people or short people, or you promote or whatever the case might be. All right. But so that's why it makes it arbitrary because that's really kind of hard to determine which direction you want to go with that. But the researcher will always tell you then at that point what's independent and dependent, so you're not having to guess. All right. So the independent and dependent variables can be plotted on a graph called a scatter plot. The horizontal axis is labeled with the name of the independent variable, scatter plot. And the vertical axis is labeled with the name of the dependent variable. So that's never changed, just like in what we've done all semester and in any other math course. The coordinate of the the coordinates of the axis are determined by the smallest to largest. Data values of the variable. Obviously, if my smallest is 1 and my largest is 10, I'm not going to go by tens. I'm going to go by 1, starting with 1. If my smallest is 50 and my largest is 732, obviously I'm going to start like at 50, and I might go by 50s or 30s or 25s, depending on how many data values I have. So that's all that's basically stating, which we've seen already. So make sure I add that extra line there. Just kidding. All right, so the definition of a scatter plot. So a scatter plot is a graph of the. Hey, this is like the first time that the definition here wasn't the blank. It finally happened in the last chapter, right? But it is the ordered pair. Yes, ma'am. Yeah, pretty much. So a scatter plot is a graph of the ordered pair of the numbers consisting of the independent variable x and the dependent variable y. The scatter plot is a visual way to describe the nature of the relationship So we're going to have a spelling test. Make sure y'all can spell relationship. Between the independent and dependent variables, even if the scales are not the same, meaning that maybe you're going by tens on the x's and ones on the y's, it can still be a visual representation. Researchers are looking for positive linear relationships when the data points increase from left to right. So you read a graph like you read a book from left to right, and a negative linear relationship when the data points decrease from left to right. Curve linear relationships or other non-linear relationships, or no relationships at all when the scatters show no pattern, line, or curve. Go ahead. To represent like a zero. Is that what you mean? Like a zero slope? Yeah. I think that's still considered no correlation because it's not pulling. No, so basically, no matter what the independent variable is changing, it's not changing the dependent value. So you would still argue that there's no correlation, even though algebraically we're like, well, that's a zero slope. Well, that would just mean a zero correlation. So no correlation. What's the question back there? Okay. So that's like a quadratic. So there's going to be we call them nonlinear, but you can see them as curve just to kind of get a head start here. But I could have data points that kind of look like that. And I'm like, well, it's not linear, but that definitely looks like it's a quadratic. And then you would call it a non-linear relationship or a curve linear relationship where it's curving. It wouldn't be positive or negative. You would have to argue it's a non-linear bell curve or a quadratic curve. So it wouldn't tell you I mean, I guess you could still determine if it is there is a way to determine if it's quadratic, and then you would have to determine the regression line. And then from the regression line, check the correlation coefficient, which again, I'll teach you later. And then that alone could tell you if there is still a relationship depending on how strong your correlation coefficient is. But that'd be something that I don't know if we go that far in this statistics course, but that's something you could definitely see. You're welcome. All right, so here's some examples of some scatter plots. I mean, they're pretty straightforward. Again, you see these dots are really close together and it's going in an upwards direction. This is called technically a strong positive linear relationship. We do have a formula to calculate this correlation coefficient to determine if something is strong or weak, because the argument's always, well, where's the cutoff between the differences? There is a cutoff, and I'll show you what those cutoff scores are and how to determine those scores. For now, just know that, if it's going up, it's a positive. If it's going down, it's a negative. Again, these are two examples that you're reading from left to right, just like you do any other book. This right here would be a non-linear or a curve linear relationship because it doesn't make a positive or a negative slope, but can show some type of quadratic look. There is some situations that's just really hard to determine if there's even a curve linear relationship. And then, of course, this is no correlation. Some might argue that might be positive due to that outlier, but if you take that outlier out, can you argue that there is a relationship or not? But again, we'll calculate what the correlation coefficient is. That will help us better determine if something is a no relationship or not. But if it's something really scattered like that, just know it's going to be a no. All righty. So procedures for drawing a scatter plot. First, draw and label your X and Y axis, just like we did with our histograms and bar charts and all the other things we've graphs at the beginning of the semester. Step 2, then plot each point on the graph, just like you would do normally. And then determine the type of relationship, if any, that exists for the variable. So once you visually graph it, then you just ask yourself, all right, is this positive, negative, no, or is it a curved linear? Does it make a more quadratic look? All right, so in example one, which I'm pretty sure is done for you, but there will be some that we will have to do, but I'll show you how the calculator can get that answer for you pretty quickly. So it says to construct a scatter plot for the data attained in a study on the number of abscesses and the final grades of 7 randomly selected students from a statistics class. So again, you do technically have 3 columns here, but we're not really focused on the student's name, even though their name is A, B through whatever. We're really focused on, does their abscess correlate to their final grade in the class, right? So therefore, your abscess will be your independent, and your final grade will depend on how many absences you have. Questions on how data will be thrown at you? Okay. Then from that, we just take those as ordered pairs. So that'd be like 6, 82, 2, 86, and so on and so on. So when you're trying to draw this out, you have your X and Y axis. The name of it's just going to be whatever the variable is called. So this is number of abscesses as my X, because that's what the independent variable was. This is my final grade named on the Y axis. This is what I would expect you to do on your finals, just be able to name it. And then you just come up with a reasonable like lineup of numbers. If I'm ranging between, like, my smallest value looks to be like a 2. Is a 2 to 15. I'm going to go by ones in that case. You might be able to argue by twos, but you have 7 data points. So you don't want things to kind of stack on top of each other. But regardless, you could do however you want. And then here, I think I start off at a 43, and then it goes up to a 90. So again, there's no need for me to start at 0, 10, 20. If 43 is my first number, I would actually argue I'd probably start at 40 and then go 50 all the way up to 100. They started at 30 just so there'd be more of a gap, but you could argue either way. You can't get really wrong with the scale, but make your work as easy and clear as you can. You don't want to be cramped packed and you're looking at data points this close to each other, right? Once you have it nice and labeled and you have it plotted, now you're going to look at it and you're going to analyze it. What kind of relationship does this have? It looks definitely like a negative relationship. You could probably even argue the non-curve, but it's really just this one outlier. So if one point is dictating between like non-linear or a negative, take that out and ask yourself the same question. What kind of relationship does that show? Negative. So that's the direction it's going to go. If you took that point out and it would still argue it's nonlinear or curve linear, then you could say at that point, all right, this is probably curve linear. Okay. So don't make one little outlier make you have a strong debate. Just take it out, relook at the data. So that's basically what they said here. So in this example, there appears to be a negative linear relationship between the number of abscesses and the final grade as a percentage. So a negative relationship here would actually mean the less absences I have, the higher my grade, or you could flip flop that, the more absence I have, the lower my grade, right? So as you can see, the more abscesses, lower the grade, or the least amount of abscesses, the higher my grade. Now, obviously, there's always those outliers like this kid here. He only missed 2 days, but still made a B. This kid here missed 5 days and still made an A. There's always going to be some outliers, but roughly speaking, even logically speaking, if you're not in class, you're not going to do well in learning. But there's always that kid that never comes to class and can still just show up and make an A, and you'll meet them in college and they'll frustrate you because you're over there studying your butt off. You're like, man, I made a B, and this kid showed up for just the test with a pencil, wasn't even prepared to study, and then just took the test and made a perfect score. And that kid, sorry, this you'll meet them. You'll meet them. There's always one. Do it. I don't think he's just better at the subject. I just think he's cheating somehow. Yeah. Oh yeah, maybe that's his second attempt in the class because he failed it the first time. I appreciate that reasoning. That's going to make me feel better at night. All right, so let's look at example 2. Again, I think they did it for us already, kind of save ourselves some time. But it says a number of teachers in the thousands and number of pupils per teacher. Pupils meaning students. So a researcher wants to check for a relationship between the number of pupils per teacher and the number of teachers in thousands employed by the school district. And the data are randomly selected. Again, the school districts are just named 1 through whatever. 1 through 10. So great names they're coming up with today. But again, I could care less about that because here I have the number of teachers in the thousands. It does not tell you if this is X or Y. And then pupils per teacher. This right here, though, we're going to assume is going to be our independent variable. And then pupils per teacher will be our Y. And then we assume that because if you remember in algebra, a chart written vertically is labeled X, then the Y. So if it does not relate that to us, then that is the assumption we make, right? If it wanted us to go the other way, then of course we would have pupils first, then number of teachers. So there's our ordered pairs. Again, write it as like 9, 14.3. We start off by drawing the label and the X and the Y axis. Oh, it did it for y'all, didn't it? Oh, it didn't? Huh, it did it for me. Okay, cool. Let's do this quickly then. So we'll draw it roughly. My X-axis is considered the what? Yep. Do tell the readers, just like we did in chapter 1 and 2, that it's in the thousands. So again, the information given to you, they should be able to pull all that from your chart rather than having to go read the paragraph itself. And then, of course, the y-axis is all right. So number of teachers, I see a 7 or I see a 6 to 34. What do you want to go by? Okay. So 6. There's no wrong answer there. 12, 18, 24, 30, 36. But again, you want to give a good space because you don't want all your data to be cram packed. So whatever number set you do choose, make sure you can space it out. Don't put them all on top of each other. And then I see for pupils per teacher, I see 9.2 to about 18.3. What do y'all want to go by? So start like at 9 and then go up by ones. That sounds good to me. So we'll start here at 9 and then we'll say 10, 11, 12. What do we have to go up to? So we'll say 19, 13, 14, 15, 16, 17. I ran out of room. Maybe we should have gone by twos. Oh well. Yeah. All right, so plugging it in, so we get 7, so that would roughly be, this is gonna be hard to do. 7 and 12.4 is roughly, I don't know, right there. 34, 14.3. Right there. 9, 14.3. 8, 9.2. I lost 16, 18.3, 15, 12.1, 6, 12.3, 'll almost be around top of that other one. 14 and 12.4, 32, and 15.2, 10, and 13.4. So roughly, that's what your graph should roughly look like. So now I want you to determine if there is a relationship or not. What would you argue? Yeah, that's what they stated as well. They said there is no positive or negative um, linear relationship here. Um, it looks really scattered. You might be able to argue maybe a positive if maybe you took out these two scatter plots, but really in general, it doesn't just seem like there's much of anything. And so this is where graph looking at scatter plots can get tricky because you can look at it and go, well, when do I make the assumption that it's a no of positive or negative? Because you could argue a certain way and then the answer be a different way of your argument. Again, we do have formulas that will determine that correlation coefficient for you. But for this one, this is going to be a no relationship or no linear relationship. Because there technically could be a nonlinear relationship. So there might be, maybe this is exponential, maybe it's logarithmic. So we can't argue those yet, but we can say definitely probably not linear. Any questions there? Go ahead. And the pupils at different districts. Yeah. Yeah. So they're arguing that if there was 7,000 teachers, there's about 9 something kids with that one. And then they're saying, well, if there's 35,000 teachers, there's about 15 kids per teacher. But then they're also arguing if there's 15,000 or sorry, 1,500, then that's 12 points. So it's hard to argue that depending on how many teachers you have will depend on how many pupils you have per teacher. All right. So in the second objective here, we're going to compute this correlation coefficient. So the correlation coefficient measures the strength of a relationship. So if you're trying to determine the strength of the relationship that you're currently in, you can run these tests to just see how strong y'all are, if it's a positive or weak, and then you can kind of see if it's positive or a negative relationship. You don't want a negative relationship. Totally kidding. It might work, but you're gonna need some data for that. You have to judge your happiness and the time you've been with the person, right? All right, so definition of population coefficient, correlation coefficient. So the population correlation coefficient is denoted by, this is spelled phi or lowercase phi. Well, it's pronunciated as phi. It's a fraternity number, PHI, yeah, but it's a lowercase p. This is going to be the correlation computed using all possible pairs. So all possible pairs. So you could do a test where it's like your significant others, past partners, see how those went, and then kind of go from there and kind of judge where y'all are going to head. I'll laugh if y'all actually do this. Data values X and Y taken from a population. All right, so linear correlation coefficients denoted by R. So this is so again, that goes back to that if it's talking about population or if it's talking about sample, population's always going to be denoted by some type of Greek letter, where a linear is going to be denoted by what I like to call regular letters. So this is an R, just like sample standard deviation was a lowercase s versus a sigma. So just know that the difference there. I don't know why I put an arrow there, but I wanted to make sure y'all knew I was talking about the R right there in that location. So a linear correlation coefficient will be denoted by the R computed for the sample measures the strength, and it'll actually also tell us the direction as well of a linear relationship, obviously. Between two quantitative variables, again, it cannot be more specific. It does have to be people. So if you're trying to determine your relationship, put some numbers with those variables of some sort. All right, so properties of linear correlation coefficients. The correlation coefficient is unit less measure. I have no idea what that means. Unitless, but it goes from -1 to 1. That to me sounds like units, but whatever. I like that. It has less units than other things because it only goes from -1 to 1. So the value of R will always be between -1 and 1. Inclusive, that means that -1 and 1 can be the answer, but it'd be all the numbers in between it. So if you ever get an answer that's outside of -1 and 1, you have done something wrong. Go back and check your work. If the values of X and Y are interchanged, the value of R is unchanged. So it'll still determine if there's a correlation between it regardless. If the values of X and or Y are converted to a different scale, the value of R again is unchanged. The value of R is sensitive to outliers though, and can change dramatically if they are present in the data. So basically, to kind of give you an idea, the closer your R is to -1, the closer to a strong negative correlation you will have. The closer you are to 1, the closer to a strong positive correlation you will have. And the closer to 0 you are, the closer to a non-linear relationship you will be at. Right. Any questions there? Makes sense. So -1 negative, 1 positive, and then of course 0 is no. So there is a scale to this. So let's look at it. So you see here you have a 0.5 for the R. So kind of see that it does a positive correlation, but it can be considered what we like to call a weak positive. And this being at 0.9 or even at a perfect score, these will both be considered strong, positive. And then, of course, this being a negative 0.5 will tell us it's a negative correlation. And being at 0.5, we would call this a weak negative. And then this would be a little bit closer knit. So both of these at -0.9 and at -1 will be considered a strong negative for both. All right. So let's fill in some more blanks. There is a breakdown on where you cut off the weak and strong. I assume we'll get to that point eventually. You like that formula? Yeah, I'm going to show you how to use the calculator though. All right, so the sample is a random sample. The data pairs fall approximately on a straight line. and are measured at the interval or ratio level, meaning decimals are included. The variables have a bivariate normal distribution. Don't know. I'm going to assume that there's two variables involved for yeah. That is given any specific value of X, then Y values are normally distributed, and given any specific values of Y, the X values are normally distributed. So be sure to check the assumptions are met with the exercise, but does not state that they will hold. So we do have a formula. And again, I don't even know what statisticians even still do this by hand. There's so much that a calculator and Excel sheet will do for you. But to calculate how to get the correlation coefficient, you would have to take the sample size times the sum of every X times Y. You would have to multiply X times Y, add all those results, and multiply that by however many samples you have. Then you would have to add up all your X's, then add up all your Y's, multiply those two. I don't know why I just said it like that, but you would you would multiply those two sums and then take the difference of those two values. That's the top part. The bottom part, you would have to take the square root of taking each X value, squaring it, adding them all up, multiplying it by however many samples you have, and then take all the X values that you have, add them all up, square that result, take the difference. That's the first part there. Do the same thing with your Y's, then multiply those two together, then take the square root of that result. And then what you did on top, you would then take it from the bottom to get your R. Pretty easy. Yeah. What? It's the correlation coefficient. It tells you how strong or weak your correlation linear, huh? Oh, N is the sample. So it's like N would be like if I had 10 people in my sample, it would be 10. So the number of data pairs right there. And we'll round to 3 decimal places with talking about R. So it is going to make you kind of go through the steps of this. So again, to kind of put in words exactly what I just did or said to y'all, place the values of X in the column X and the values of Y in the Y column. Then you're going to multiply each X value by the corresponding Y value and place the products in the XY column. Each X value, sorry, my bad, then square each X value and place the squares in the X squared column. Then square each Y value and place the squares in the Y squared column. Then you're going to find the sum of each column. Very good. Then you're going to substitute all of those answers into the formula as follows, and then round your answer to 3 decimals. Correct. Yeah. So in this one, it's kind of already done for you. So I will show you that part, but I will show you the quicker way. So here's all of the researchers' X and Y values. They placed all the independent and dependent variables in. Then they took each pair and they multiplied it. That's how we got to these numbers here. So 6 times 82 is 492 and so on and so on. Then we squared each of the X values. So 6 squared is 36. Then we took all the Y's and squared them. So 82 squared is 6,724. Then once we had all of the columns filled out, we then added each column up. That's what these things right here mean, is the sum of those columns. Once we have all those E's, we were able then to plug it all into this equation. So then you get an equation that looks roughly like this. And when you do all the math, you get a negative 0.944. So we could say, what could we argue on this assumption then? Good, a strong negative linear correlation, right? Do what? Say what? Yeah, that's what it could have just asked for the R, right? Yeah, that's what I'm going to teach you is how to do this in the calculator. Yes, like I don't even recall ever. I think no, I take that back. I do recall one professor that did hate calculators. So we had to do it by hand, but it was like 10 units. So, but he always said, if you do one, then you'll appreciate the calculators. I was like, okay, but no one in our time does that anymore. All right, so let's look at this example here. So it says we're going to take the values from example 10.2. I'm not going to fill out this chart. I'm just going to tell you how to get to R. All right, so this is what you're going to do. You're going to pull out your handy dandy calculator, or you can use Desmos. Both of them does the same. Oh, it's not the one I wanted. Yeah, but for homework purposes. Or Excel works just as easy. I think with Excel, you can literally just type in correlation or something. I don't know if you have to spell out the whole word, but then you just say between the two columns and done. So again, we're looking at example 10.2. So where's 10.2? 10.2. Yeah. So 10.2 is the teachers. All right. So first thing you're going to do, just like everything, we're going to go to list and spreadsheets. I'm going to let this be, ooh. Let it be X. Got to give it a name. You have to have points first. So we're going to put points in it so that it graphs it for us. So here we go. So 7, 34, 9, 8, 16, 15, 6, 14, 32, 10. Example 10.2 on page 5. I think 5. It's the teachers and pupils. I think it's on page 5 for y'all. A little both. Again, don't forget to name your columns X and Y. That's going to be very important for this next step. Sorry, I was getting ahead. Let's see if I can do this quicker. I can. I can. I don't even have to go to the other thing. All right. So we don't even have to go to the data and spreadsheet. Does everyone have it? I guess you don't even have to give it a name now. Always curious. Yeah. If you didn't name it, it's not going to be no stress. Has everyone got it in? Do believe so. All right, here we go. So you're going to just go to menu once the data is in. And then this is a statistics course. So you can go to statistics. Then we're doing stat calculations. So you want to go to stat calculations. We have two variables. independent and dependent. So you'll go to a two variable statistics. You'll call your X the A column, call the Y the B column, then simply just go hit OK. I didn't. I mean, I named it. What did I do? I just did it. Let's try X and Y. I just did it. Okay. Maybe you're right. Maybe you have to put an X and Y. I just did X and Y once it didn't work for my A and B and then printed it. I printed it. Just hit OK. Oh, did you stop? Did you hit the enter button after you're done typing? Syntax error also could mean that you put a letter or something where the equal sign is.
A bracket.
Oh, that's all your answers.
Yeah, he had a problem.
Oh,
We're done.
yeah. Why you got extra numbers?
I don't know.
You didn't finish typing. Anyways, the R is given to you if you just scroll down a little bit.
Hey,
No.
I didn't do these two.
No, you didn't do these two. No, wait, you're right.
No. I moved them all up. I didn't do these two. I just started from here.
Oh, and that's gonna put a big difference in it. But I guess is that the bell's ending? Gotcha. But the R is just the one that says R. So if you just scroll down, there's your R right there. So therefore, that right there is your correlation coefficient, which is 0.442. So this would be an indication that it's a positive, but I would argue a weak. And that's pretty much it. All right, a couple of things. I'm not going to discuss regression. I'm going to take 10.2 out, so you only have 10.1 homework to do. All right. I don't know if I'll get to see you tomorrow. Huh? That's not a bad idea. I'll take 10.2 to replace your lowest daily grade that you've made all year. If you have all 100s, that's hard. Oh, I don't know. I tell you what, if you have all 100s and then you did 10.2, each thing is, I get 4 points on the upcoming final exam. Where's my Zoom? Yeah, so I'm going to look at the homework and see what questions I didn't get to.